counters. So the counter is an application of the flip-flop. Okay. So what is a flip-flop? Flip-flop is a storage device which has 0 and 1 combination. So it's an example of a register. The primary purpose is to produce a specified output pattern sequence. It is also called pattern generator. Okay, counter may be a up counter or a down counter. If suppose example a counter is a 3-bit counter, means it will generate from 000 up till 111. It is a 3-bit up counter. Okay, 3-bit down counter, it counts from 111 to 000 and again roll backs to 111, next up till 000. Particular pattern it generates. Okay, specified output pattern sequence. So it is also called pattern generator. Each stored 0-1 combination is called state of the counter. Whatever 0-1 combination will be stored in the counter, and that stored is known as state of the counter, or that particular sequence is called the state of the counter. The total number of state is called its modulus. So total number of state is also known as modulus. If the counter has m distinct states, then it is called mod m counter. If suppose it has 8 different states, so it is called as mod 8 counter. The order in which the states appear is referred to as its counting sequence. The order in which, that is for example, if I have a 3-bit counter 0000001 up till it will count 111 and then again roll back to 000 and again it will count 001 up till 111. So this is known as a counting sequence. The order in which the states appear. This is 0 state, this is 1 state, this is state 7. So totally how many states are there? 8 states are there, right? 8 different states are there. So this is known as mod 8 counter or 3-bit counter, and this is known as counting sequence. It counts from 000 up till 111. So the counting sequence is depicted by
Excuse me, ma'am.
directed graph. Yes, 1 minute. So here the counting sequence is depicted by a directed graph known as state diagram. Okay. So state diagram of a counter. So this SI denotes one of the states of a counter. See now here, what is this? A circle written inside S1. What does it define? This is in the state 1. The counter is in the state 1. Next it goes to state 2. Next it goes to state 3. Next it goes to state 4. Similarly up till SM, that is mod M counter, has M different states. So what is this? This is a state diagram of a counter. A circle with a S1 written shows that the counter is in state 1. Next it goes to state 2. Next state 3. Next state 4. Up till next dot 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 up till SM. M. Okay, so this is how we need to write a state diagram of a counter. SI denotes one of the states of the counter. Arrow in the graph denotes the order in which the state occurs. The order in which means first state 1 occurs, in the next order, in the order sequence, next state 2 occurs, next in the order state 3 occurs up till SM. Okay, so this is the order and this is the counting sequence which the counter is following. A particular pattern sequence is generated by a counter. Okay. So binary ripple counter. Here in this, the counters whose counting sequence corresponds to that of a binary numbers are called binary counters. Means the sequence, the counting sequence which is having a binary number sequence. Okay, binary numbers means 000, 001, 010, 011. Okay, those are all binary numbers, and the counters whose counting sequence corresponds to binary numbers are called binary counters. Modulus is 2 raised to n. Okay, where n is the number of flip-flops in the counter. Okay, we have in the counters binary up counter and binary down counter. Okay, so binary up counter, I had told you that binary up counter 0 0 0 0 0 1 0 1 0 up till 1 1 1 it will count, and then again it will roll back to 0 0 0 0 0 1 0 1 0 up till 1 1 1. This is a 3-bit up counter. Similarly, you can have 4-bit up counter also. Okay, with the 4 bits up till 1 1 1 1. Again, then it will roll back to 0 0 0 0. This is 4-bit binary up counter. The counting sequence is binary number, hence it is a binary counter. It is counting in the upward fashion 0, 1, 2, 3 up till 15. Next, binary down counter, if it is a 3-bit counter, it will count 7, 6, 5 up till 0, 0, 0. After that, it will roll back to 1 1 1 1 1 0, that is 7 6 5 4 3 2 1 0. Then again back to 7 6 5, like this it will count in a downward manner, hence it is binary down counter. It can be 3-bit, 2-bit, 4-bit. Okay, it can be n-bit. So next, coming to very important part, 4-bit binary ripple counter. Recall the positive edge triggered T flip-flop. We have already studied the T flip-flop in the previous class. Okay, each positive transition from logic 0 to logic 1 causes the flip-flop to toggle. Here, recalling the T flip-flop, T and the output. Okay, so when you apply a clock, it is a positive edge triggered. Okay, so when you apply a clock, if T is 0, the output will retain QQ bar. That is, it will retain the present state. I am talking with respect to T flip-flop, the functioning of the T flip-flop, the function table. If the T input is 0 and when I apply the clock, it will retain the present state. If T input is 1 and if I apply the clock, the output will toggle. It becomes Q bar and Q. If it was 1, it will become 0. If it was 0, it will become 1. That it will toggle. It will switch. If it is 1, it will toggle to 0. If it is 0, it will toggle to 1. This is the function table of the T flip-flop. If T is 0, it will retain the present state. If T is 1, it will toggle. If it is 1, it will become 0. If it is 0, it will become 1. It will toggle when T input is 1. Now here, how many flip-flops are there? 4 bits, right? So it is a 4-bit binary ripple up counter. Okay, it is a 4-bit binary ripple up counter. Up counter, why? See here the counting sequence 0, 0, 0, 0. Next it is 0, 0, 0, 1. So 0, 1, 2, 3, 4, 5 up till 1, 1, 1, 1. Again it will roll back to 0 and next it will start counting 0, 1, 2, 3 up till 15 and then again it will roll back to 0. So this is 4-bit binary ripple counter. So let me explain this now. So here you can see here the count enable is there. Here the count enable is applied to this T input of all the flip-flops. Here this is a count enable. Here from here it is applied to the first flip-flop. Next it is applied to second flip-flop. Next it is applied to third flip-flop, and here it is applied to the fourth flip-flop. Next you can see here, okay, the count pulses, that is the clock. C is a clock, okay. This is the T, it is the input. Q is the output, Q naught. And this is Q naught bar, okay. And this Q is Q1. This is Q1 bar. And this is Q2. This is Q2 bar. This is Q3. This is Q3 bar, okay. You can see here the one of the observation you should do here is the Q bar is connected as an input to the clock of the next flip-flop. Here also Q1 bar is connected as an input to the clock to the next flip-flop. Similarly, the Q2 bar is connected as an input to the clock of the next flip-flop, right? So whenever the count enable is 1, this counter will work, okay. So initially let me assume all are 0, 0, 0. Next I will apply the count pulses, okay. So if T becomes now, okay, so T was 0 now previously, assuming the initial state it is 0, 0, 0, isn't it? So now apply the count pulses, apply the clock, okay. Now T becomes, I will apply the count pulse 1, it will become 1, okay. So 1 means it will toggle, I have explained here, 1 means it will toggle, okay. So previously it was 0, now it will become 1, isn't it? Now it will become 1. So Q naught becomes 1, Q naught bar will become 0. So this 0 is applied as a clock to this next flip-flop. So if clock is 0, okay, so here what happens? This will not work. It will not work. So it will be 0. So if this will not work, this will not be affected. If this will not be affected, this will not be affected. So it will retain the earlier position only, okay. Is it okay? Next, again I will apply the count enable. This will become 1 now. Next this becomes 1 means, right, this 1 will become 0. If this becomes 0, this will become 1. So this 1 will come here, okay. Count enable is applied 1, okay. So 1 means it should toggle. So this becomes 1, whereas this becomes 0. So this 0 is applied as a clock to this, isn't it? So this will not be affected. So if this is not affected, this will not be also affected. It will retain the earlier state only, okay. This was also 0, this was also 0, okay. So next again I will apply the count enable now, count enable. So this will be 1 now. So this becomes 1, this becomes 0 itto 1 aitto, this becomes 1. If Q naught is 1, Q naught bar is 0. If this is 0, this clock is 0, this will not work. If this will not work, this also will not work, because this is connected, the output Q1 bar is connected as an input to this clock, right. So this will not work, it will retain the previous state, okay. This will not work means this is also affect this will also not work, so it will retain the previous state. If this will not work, this also will not work, it will retain the previous state. Is it clear? Right? So similarly up till 1, 1, 1 it will toggle, okay. So you can see here, this is a state 0, this is state 1, this is state 2, this is state 3 up till state 15. Whenever it reaches 1, 1, 1, 1, what happens? All the flip-flop all will be 1, all will toggle. 1 becomes 0, 1 becomes 0, here 1 will become, then again 1 will become 0, so again 1 will come here, and again 1 becomes 0 here, so this will be 1, again this will come here. isn't it? So this here what happens is asynchronous type of flip-flop counters, because the output of the one of the flip-flop is connected as an input to the next, output of second flip-flop is connected as an input to the third, output of the third flip-flop is connected as an input to the fourth. This is a asynchronous. This flip-flop will affect this flip-flop will affect this. Until and unless you don't get the output of the first flip-flop, second will not work. Until and unless you don't get the output of the second flip-flop, third will not work. Right? Until and unless you don't get the output of the third flip-flop, fourth will not work. Okay. So in this way, it will count the 0 0 0 up till 1 1 1. Whenever it becomes 1 1 1, it will toggle from 0 0 0 0. Again, next the counting sequence starts. Right? So you should see like this: 0 0 0 0, state 0. 0 0 0 1, state 1. 0 0 1 0, state 2. 0 0 1 1, state 3. Right? So when the flip-flop will trigger, when the complement Q0 bar is 1, that time clock will be applied to the second flip-flop. Next, here Q1 bar should be 1, then only it will apply, then will only this flip-flop will be active, because Q1 bar is connected as a clock input to the third. Next, Q2 bar should be 1. If Q2 bar is 1, then Q2 will be obviously 0, right? So here Q2 bar should be 1, then only this clock will be active. If clock is active, then T flip-flop will be active. In this way, it will count from 0 0 0 up till 1 1 1, that it will roll back to 0 0 0, right? Okay. So this one we need to explain it in the form of a timing diagram. So this will be triggered when Q0 bar is 1, when Q1 bar is 1, when Q2 bar is 1, like that, right? So obviously if Q0 bar is 1, Q0 should be 0. If Q1 bar is 1, Q1 should be 0. Q2 bar is 1 means Q2 should be 0. Okay. So here, whenever the count pulses is 1, the count pulses is 1. See here, whenever Q0 is 0, that time it will be, Q1 will be triggered. Whenever Q1 is 0, Q2 will be triggered. Whenever Q2 is 0, Q3 will be triggered, right? So here these counting pulses, I am giving the data here. So Q0 bar, Q0 is 1 means Q0 bar should be 1, not to trigger. In the previous flip-flop, in the previous we have seen here, Q0 should be 0, Q0 bar should be 1 in order to be active, isn't it? Once again I am telling, Q0 should be 0, Q0 bar should be 1, then only the Q1 will be, this second flip-flop will be active, that is Q1 output. So here you should see here, whenever Q0 bar is 1, that is here Q0 should be 0 for Q0 bar to be 1. So for the negative of the Q0, Q1 will be triggered. For the negative of the Q1, Q2 will be triggered. For the negative of the Q2, Q1 will be triggered. Okay. So here, how do you do the counting sequence? 0, 0, 0, 0. Right? Next 0, this is 0, this is 0, this is 1. Next 0, 0, 1, 0. Like this, you should see like this vertically 0, 0, 0, 0. State 0. Next 0, 0, 0, 1. State 1. 0, 0, 1, 0. State 2. Next 0, 0, 1, 1. State 3. Next 0, 1, 0, 0. State 4. Isn't it? 0, 1, 0, 1. Similarly up till this 1, 1, 1, 1. Okay. So how do you call this now? 0, 0, 0, 0. State 0. 0001 state 1, 0010 state 2, 0011 state 3 up till 1111 state 15. Then it will roll back to 0000 up till 1111. Again it will roll back to 000. This is the waveform. Okay. Next, talking about the 4-bit ripple up counter known as a ripple. Ripple means the output of the next flip-flop is dependent on the output of the previous flip-flop. The output has to ripple through all the flip-flops. Ripple counter, since a change in the state of the Qi-1 flip-flop is used to toggle the Qi flip-flop. The previous flip-flop output is affected by the next flip-flop, right? Qi-1 flip-flop is used to toggle the Qi flip-flop. The effect of a count pulse must ripple through the counters, isn't it? Ripple counters also referred to as asynchronous counters. Asynchronous, why? Because the output of one of the flip-flop is connected as the input to the next flip-flop. Okay, so the output should ripple through all the flip-flops. Propagation delay. There is a propagation delay between the input and output of a flip-flop. Rippling behavior affects the overall time delay between the occurrence of a count pulse and when the stabilized count appears at the output terminals. What is the worst case of the propagation delay? Going from 1111 up till 000. Since all are toggling in this condition from 111 up to 000, toggle signals must propagate through the entire length of the counter. Right? This is the worst case delay. So going from 111 to 000. For n-stage binary ripple counter, the worst case time is n into TPD, where TPD is the propagation delay time associated with each flip-flop. Okay. So this is about the 4-bit ripple counter.